Hello and welcome to another video where we're going to be looking at the MAT 2013 and the first 5 questions. So without further ado, let's have a little go at it. So what have we got here? For what values of the real number a does the quadratic equation have distinct real roots? Well, distinct real roots, I'm immediately thinking the discriminant, but not before I rearrange this into, quadratic equals 0 form. And then I can use now, like I say, distinct real roots. Well, that is where, and I'm going to put this inverted commas just because the BA and the C represent different things to what A is up here. But B squared minus 4AC, I need that to be bigger than 0 for the roots to be real and distinct. And that's just a fact you should know. So we'll take our B squared, which in this case is A squared, and then we'll do minus 4 times 1 times by A minus 1. And that needs to be bigger than 0. And so what we've got here, A squared minus 4A minus 4 is bigger than 0. Well, that's going to be the case when A minus 2 all squared is bigger than 0. Yeah. Now, we need this to be bigger than 0. That's what we need. But actually, there's a number I can plug in here for A, which makes this equal to 0, which means the inequality doesn't hold. So this is true unless A equals 2. In other words, it's going to have distinct real roots in every case, so long as A doesn't equal 2. And so if I can just ring this answer, I believe it's going to be A. As long as A doesn't equal 2, it will have distinct real roots. Yeah, that's what this is telling you here. Does that kind of make sense? I hope it does. It's if A doesn't equal 2, then you're fine. But if A equals 2, then it's all gone wrong. It won't have distinct real roots. It'll have equal roots actually, because that would make that equal to 0 if A equals 2. If A equals 2, it has equal roots, so it's not distinct and real. Okay, so that's the first one done. Let's try the next one. What we got here? We've got the graph of y equals sine x. So let's actually draw a graph of y equals sine x here, just a dodgy little graph. It will help. It will, it doesn't have to be perfect. You just need to be able to use it effectively. Okay, now what are we doing here? We're reflecting it first in the line x equals pi. Well, pi is here on a typical sine x graph, and if we reflected it in that line, maybe it would help if I kept on going just to give you a general idea. If we reflected that in that, well, what's it going to give us? Well, I'll draw a reflected curve. Clearly, that's going to be over here, but this is going to be under here, and that's just going to keep going like it was. In other words, you're going to end up with sine of minus x, essentially. You've reflected it in the line x equals pi, but it's exactly the same as reflecting it in the y-axis, actually. So we get that after reflection in line x equals pi. And now we're reflecting it, and then in the line y equals 2. So it might help to draw it out again, actually. Like, you just need a couple of lame diagrams here. Let me do this in black again, just to make it a little bit clearer, perhaps. So I'm just going to draw the graph after it's been reflected. So we know that sine x has suddenly turned into the upside down sine x, if you like, after reflecting it. It's going to be underneath there. I'm drawing the red one really down here, if you see what I mean. So this is, after a reflection line x equals pi, and actually it's got the equation sine of minus x, or minus sine of x, depending which way around you want to look at it. It's actually minus sine x. But what are we doing now? We're reflecting in the line y equals 2. So bear in mind this is at 1. And, I haven't really left myself enough space here. But I hope you can see this. Let me just try and do it down here. If this was like the current state, and that's 1, and you're reflecting it in 2, clearly this one is now going to be up. If you reflected it in that line, it's going to be up there, yeah? And it's going to be upside down, so it's going to look like that. Yeah, and the same for this one. As that's like 3 away from 2, it's going to be right the way up here. Oh, it's actually really messy to draw this, especially with my dodgy drawing on a graphics tablet on the whiteboard. Let me try again, because you need to see it. And I apologize, but it's really hard for me to keep a steady hand on a graphics tablet, so I do apologize for that. I'm going to try and draw it as flat as possible so I can squeeze it all in. So your 1 is here. Your 2 is the line you're reflecting it in. And clearly, if you reflect that in there, then the origin is suddenly going to be at 4, because it's going to be the same distance. And actually, this is going to be going down now. And that's going to be going up. Well, can you see that what you've got here is essentially sine x, but moved up 4, because it's going to be oscillating between 5 and 3, and that is a sine x graph of, after it's just been moved up 4. It's the original sine x just moved up 4, and that's why this one is just y equals 4 plus sine x. It is possible to do this algebraically. There's no doubt about it. It's definitely possible to do it algebraically. I prefer, though, to just do it with the graph and function transformations myself like that. If you want to do it algebraically, though, fair play, go for it. That's absolutely fine as well. I think it is easier with a graph. So, okay, so that was a graph. So I apologise for my terrible drawings there, but that's the way I see it. I hope it makes sense as well with where it's going. Okay, right, let's do another one. Part C. What do we got here? Okay, yeah, so this looks like a function kind of one where they've got, it's one of these abstract function kind of questions. We need to find f double dash of x. We know f dash of x, but we need to find f double dash of 2x. So first, let's write down what f dash of 2x is. Now that's simply going to be replace x with 2x over here. So I'm going to replace x with 2x. Yeah. And now if I want to differentiate this, I do need to use the chain rule. Yeah. So I'm going to differentiate inside the function, and that's going to differentiate to 2. And then I'm going to differentiate f dash of stuff, and it differentiates to f double dash of the stuff. Yeah, so I'm going to get f double dash of the 2x. Yeah. Now that's clearly the same as 2 times I already know that f double dash. Oh, hang on. Yeah, it might be wise to make this a little bit clearer. Hang on a second. If we just take a step back in a second here. So I need to differentiate inside the function. I'm going to get 2, and I'm going to differentiate f dash of stuff, which gives me f double dash of the stuff. And what I'm doing is I'm differentiating both sides here with respect to x. And so here I'm going to differentiate inside the function. I get a 2, and then I'm going to differentiate g of the stuff, which gives me g dash of the stuff. Essentially what I'm doing there is I'm using chain rule. But as you can see, the 2's actually cancel here. Now we still need f double dash of 2x in terms of h, as you can see down here. So let's just note that f double dash of 2x is going to be equal to g dash of 2x plus 1. Yeah, so the 2x has been replaced with the x essentially. Now we need to relate this to h. Now g dash of x is h of x minus 1. So g dash of 2x plus 1 is going to be equal to, well, let's replace x with 2x plus 1. And then we've got a minus 1. And so that's h of 2x. And so this equals h of 2x. And so the answer is C. I hope that makes sense. It's quite abstract, that one. Essentially, I'm using chain rule with the functions there, but both the 2's either side, they cancel. So yeah, it works kind of nice in the end. It really does. I suppose another way of doing it, there's several ways of looking at this. Can I just show you? You could have got the answer in other ways. Maybe you didn't like my way of doing it, but I'm guessing that you might have done it correctly, but like this. If you find f double dash of x first, we just simply differentiate both sides. Well, once again, you do need chain rule here technically. Differentiate x plus 1, though, you're going to get 1. And so you're just going to get 1 times g dash of x plus 1. But this still leads to the same answer because, once again, now we just replace x with 2x. So we can see f double dash of 2x, therefore equals g dash of 2x plus 1. Do you see what I mean? You still arrive at this result, but without the 2's popping out. You may have done it like that. You may have looked at it like that. Oh, I'm just going to differentiate this first and then plug into 2x. I plugged into 2x first, then differentiated. It really doesn't make any difference. Okay, right. So I hope that one's clear. This isn't going to work really any differently either because we just use that directly. So I'm getting a C for that. So what have I got so far? I've got A, C, C. We'll check these in a second because I've written down the answer key somewhere. Okay, what about this one? Okay, this one's kind of good fun. Straight away I'm looking at that and I'm just thinking, oh, it's dying for a difference of 2 squares factorization in some ways. X squared minus y, x squared plus y equals 2y plus 1. I don't know if this is the most sensible way of looking at it, but just, straight away when I see an opportunity to use difference of 2 squares, I tend to do it. What am I thinking with an equation like this? Well, firstly, I often like to rule out certain things. And so I'm thinking, this looks like when x is 0, y is a particular, when y is 0, x takes particular value. So if I set y equal to 0 in this, what do I get? Y equals 0. then x to the 4 equals 1. Yeah, and that means that x equals plus or minus 1. Yeah, so well, this is, that's ruled out this one because this seems to suggest that y can't be 0, that first one, because look, y is never 0 because the curve never hits the x-axis. But yet when we place y equals 0 in this equation, we get x equals plus or minus 1. And so that first one definitely isn't the case. But the other three are in play because maybe the ones are here, 1 and minus 1 are here and here, or maybe they're in there, or maybe they're there and there. So 3 in play still. So we've got that. But what about if we did it the other way round and we said x equals 0, because on this one x does equal 0, on this one x equals 0, on this one x equals 0. Let's see what happens with x equals 0. We're going to get minus y squared equals 2y plus 1. And so in other words, 0 equals y squared plus 2y plus 1. And that naturally factorizes to y plus 1 all squared. Now that's interesting because that only has one answer, and that is x equals 0, y equals minus 1. We can't have y equals 1 here, which rules out this one actually. And it rules out that one, doesn't it? Because we've got two y values for an x value of 0. And so by the look of it, the answer is B. And so I guess that answer is B. We'll check these all in a second. Like I say, I've got the answer key somewhere. Okay, so that's that one. Now, what about E? Ooh, let's have a look at this. So initial thoughts. Whenever you differentiate a polynomial of degree n, the derivative will have degree n minus 1. Do it again, the derivative will have n minus 2. But on the face of it, that would make this question super, super, super easy and fast because, that's x to the power of 4 times by x to the power of 5, which is x to the power of 9. Differentiate it twice, and you obviously get like an x to the power of 7. Yeah. And here you've got x to the power of 4 times by x to the power of 4, because x squared squared is x to the power of 4. But after you differentiate, you're going to get x to the 7 there. So you might be tempted to go with C7. But the fact that I can do that so quickly, basically in my head, and yet it's the 5th question on the paper, tells me that's probably not true. They want you to do that. That is the naive approach. But how do we know that after differentiating, that x to the power of 7s don't cancel? That's what probably happens. Yeah. And let's just prove that it does, because I've done these questions earlier and I believe that it does. If you just quickly run through this, we're actually differentiating twice. Well, what have we got here? 2x all to the power of 4. That's going to be 16x to the 4. I'm only interested in the highest power here. Only interested in the highest power. Then minus x to the power of 5. Well, that's going to go to minus x to the 5. Oh, and let's not forget, sorry, that when we expand out these brackets, we do actually need our binomial coefficients. Now, we don't need to worry about the minus x to the power of 5, and we don't need to worry about the 2x to the power of 4 here, because that's going to be the highest power. So I think that's going to be all right, but after we differentiate that twice, what are we going to have? We're going to have, well, let's just actually simplify it first. And I'm just looking at the first term here. We've actually got minus 16x to the 9. Differentiate that twice, you're going to have like 9 times 8 times by minus 16x to the power of 7. Do you know what I mean? Because the power is going to come down, and then you're going to have 9 times minus 16 times x to the power of 8. But then the power is going to come down again, so you're going to have 9 times 8 times minus 16x to the power of 7. Now, let's have a look at this bracket. Do we get a very similar term which cancels and therefore end up with D? Let's have a look. 2x to the power of 4. Well, that's going to be 16x to the 4 times by, well, we've got 3x to the power of, well, 3x squared, but then we're squaring that. So that's actually 9x to the power of 4. Yeah. And we're differentiating this once. So let's just simplify this. So we're going to get 16 times 9 x to the power of 8. When we differentiate it, we're going to get 16 times 9 times 8 x to the 7 after we've differentiated it. Oh, look, the coefficients are the same, but one's negative, one's positive. Therefore, the x to the power of 7 cancels, and the answer is D, less than 7. So I think those are the answers to the first 5. What have we got? We've got, starting from the top, A, C, C, B, D. I've got the answer key written down here. What was it? A, C, C, B, D. We've got it all right. Well done us. And that's the first 5 questions of the MAT 2013. Hope you enjoyed the video and found it useful. Keep up the hard work. Bye-bye.